What if the very fabric of the universe is hiding a secret so profound that it could rewrite everything we think we know about existence? Picture this: an invisible force, silent and unseen, is stretching the cosmos apart at an ever-increasing speed. This isn't science fiction, it's the reality of dark energy, one of the greatest enigmas in modern science. Welcome to the cosmic dark energy era, a chapter in the universe's story that challenges our understanding of space, time, and the very laws of physics. Over the next few minutes, we'll dive into 25 mysteries surrounding this elusive force, from its role in the accelerating expansion of the universe to its potential connection to the fate of everything we see and don't see. Are you ready to unravel the secrets of dark energy and explore the questions that keep cosmologists awake at night? Let's begin this journey into the unknown. Now turning to the first mystery of the cosmic dark energy era, let's explore the startling discovery that the universe isn't just expanding, it's doing so at an accelerating rate. This revelation, made in the late 1990s, turned cosmology on its head. Scientists observed distant supernovae, the explosive deaths of stars, and found that they were dimmer than expected. This dimness suggested that these supernovae were farther away than they should have been, indicating that the space between galaxies is stretching faster and faster over time. The culprit behind this cosmic speed-up, dark energy, an invisible force that seems to permeate the fabric of the universe, pushing everything apart. But what does this mean for the fate of the cosmos? If dark energy continues to dominate, the universe could face a future where galaxies drift so far apart that they become invisible to one another. Stars and planets might eventually be torn apart in a scenario known as the Big Rip. Yet the most baffling question remains: why is this acceleration happening? The laws of physics as we know them struggle to explain this phenomenon. Is dark energy a property of space itself, or is it something entirely new waiting to be discovered? This mystery not only challenges our understanding of the universe, but also hints at the possibility of entirely new physics waiting to be uncovered. As we continue to probe the cosmos, the accelerating expansion stands as one of the most profound puzzles of our time. Now shifting our focus to the second mystery, we delve into the heart of the question: what exactly is dark energy? Despite its profound influence on the universe, dark energy remains one of the most elusive concepts in modern science. Scientists have proposed several theories to explain its nature, but none have been definitively proven. One of the leading ideas is the cosmological constant, a concept first introduced by Albert Einstein. This theory suggests that dark energy is a property of space itself, a constant energy density that fills the vacuum of space and drives the universe's accelerated expansion. However, this explanation comes with its own set of challenges, particularly when it comes to reconciling the predicted energy density with what we observe. Another compelling theory is quintessence, a dynamic form of dark energy that changes over time. Unlike the cosmological constant, quintessence is thought to be a field that permeates space, similar to the Higgs field, but with properties that cause the universe to expand faster as time goes on. This theory offers a more flexible explanation for the behavior of dark energy, but it also raises new questions. For instance, if quintessence exists, why haven't we detected it directly? And how does it interact with other forces and particles in the universe? The uncertainty surrounding dark energy's true nature is what makes it such a captivating mystery. It challenges our understanding of fundamental physics, forcing us to reconsider what we know about gravity, space, and time. Could dark energy be a sign that our current theories are incomplete, or is it pointing us toward entirely new laws of physics that we have yet to discover? As we continue to explore this enigma, one thing is clear: dark energy is not just a puzzle for cosmologists, it's a gateway to understanding the very fabric of reality. And with every new discovery, we inch closer to unraveling its secrets. Now turning to the third mystery, we encounter one of the most perplexing challenges in modern physics, the cosmological constant problem. At its core, this issue revolves around a staggering discrepancy between the predicted value of the cosmological constant, the theoretical representation of dark energy, and what we actually observe in the universe. According to quantum field theory, the vacuum of space should be teeming with energy, contributing to the cosmological constant. However, when scientists calculate this energy based on quantum mechanics, the predicted value is astronomically larger, by a factor of around 1 followed by 120 zeros, than what we measure through observations of the universe's expansion. This enormous mismatch is often referred to as the worst prediction in the history of physics. So, why does this matter? The cosmological constant problem isn't just a minor hiccup in our understanding of the universe, it's a glaring sign that something fundamental is missing from our theories. It highlights a deep tension between quantum mechanics, which governs the behavior of particles on the smallest scales, and general relativity, Einstein's theory of gravity that describes the universe on the largest scales. These two pillars of modern physics, while incredibly successful in their own domains, seem to clash when it comes to explaining dark energy and the cosmological constant. This discrepancy suggests that either our understanding of quantum vacuum energy is incomplete, or there's a flaw in how we're applying general relativity to the cosmos. The implications of this problem are profound. If we can't reconcile the predicted and observed values of the cosmological constant, it could mean that our current theories need a major overhaul. Some physicists speculate that a new framework, perhaps a unified theory of quantum gravity, might be necessary to bridge the gap. Others suggest that dark energy might not be a constant at all, but something that evolves over time, adding yet another layer of complexity to the mystery. Whatever the solution, the cosmological constant problem serves as a stark reminder of how much we still have to learn about the universe. It's a puzzle that not only challenges our understanding of dark energy, but also pushes us to rethink the very foundations of physics itself. Now shifting our focus to the fourth mystery, we encounter what cosmologists call the coincidence problem. This puzzle revolves around the curious observation that the densities of dark energy and matter in the universe are strikingly similar in magnitude during our current cosmic era. At first glance, this might not seem like a big deal, but when you consider the vast timescales and the dynamic nature of the universe, it becomes a head-scratcher. Why, out of all the possible moments in cosmic history, do we find ourselves in an era where these two dominant components of the universe are so closely matched? To put it into perspective, dark energy and matter have evolved very differently over time. In the early universe, matter was the dominant force, driving the formation of galaxies and large-scale structures. Dark energy, on the other hand, was negligible back then. Fast forward to today, and dark energy has taken the lead, accelerating the expansion of the universe. The fact that we happen to live in a time when these two are roughly equal in influence seems, well, coincidental. And in science, coincidences often point to deeper truths or gaps in our understanding. So, why is this considered a problem? Because it challenges our expectations. If dark energy and matter evolved independently, the odds of their densities being so close at this particular moment in cosmic history are astronomically low. This has led scientists to question whether there's something more fundamental at play. Could this coincidence be a clue to a deeper connection between dark energy and matter, or is it simply a matter of timing with no deeper significance? One intriguing explanation comes from the anthropic principle, which suggests that the conditions we observe in the universe are the way they are because they allow for the existence of life. In other words, if dark energy and matter weren't balanced in this way, we wouldn't be here to observe it. While this idea is compelling, it's also controversial, as it leans more toward philosophy than testable science. Another possibility is that dark energy isn't constant but evolves over time. Some models propose that dark energy's density changes in a way that naturally aligns with the density of matter at certain points in cosmic history. If true, this would mean the coincidence isn't random, but the result of an underlying mechanism we've yet to uncover. The coincidence problem reminds us that the universe is full of surprises, and even the simplest observations can lead to profound questions. Whether it's a hint of a deeper connection between dark energy and matter or just a quirk of cosmic timing, this mystery continues to push scientists to rethink their assumptions and explore new ideas. And as we'll see in the next mystery, the role of dark energy in the early universe adds yet another layer of intrigue to this cosmic puzzle. Now, as we venture deeper into the mysteries of dark energy, we turn our attention to its potential role in the early universe. Could dark energy have been at work during the universe's infancy, shaping the cosmos in ways we're only beginning to understand? This question takes us back to a time when the universe was a fraction of a second old, during a period known as inflation, a rapid expansion that set the stage for everything we see today. Inflation is one of the most pivotal moments in cosmic history, stretching the universe from a tiny speck to an enormous expanse in an instant. But here's the twist: while inflation is driven by a different form of energy, some scientists wonder if dark energy might have played a supporting role. Could dark energy have influenced the early universe in subtle ways, leaving behind clues that we're only now starting to uncover? Detecting dark energy's fingerprints in the early universe is no easy task. The cosmic microwave background, or CMB, is our best window into this ancient era. This faint glow of radiation left over from the Big Bang holds a treasure trove of information about the universe's early conditions. But teasing out the influence of dark energy from this data is like trying to hear a whisper in a crowded room. The signals are incredibly faint, and other processes, like the behavior of matter and radiation, dominate the scene. One of the biggest challenges is distinguishing between the effects of inflation and any potential contributions from dark energy. Inflation left its own distinct marks on the CMB, such as tiny fluctuations in temperature and density. If dark energy had any role, its influence would be intertwined with these patterns, making it incredibly difficult to isolate. Scientists are constantly refining their models and developing new techniques to sift through the noise, but so far the evidence remains elusive. This mystery ties into a broader question about the history of the cosmos. Has dark energy always been a constant force, or did it evolve over time? If dark energy played a role in the early universe, it could mean that its properties have changed dramatically since then. This would challenge our current understanding of dark energy as a steady, unchanging presence and open up new avenues for exploration. As we piece together the story of the early universe, the role of dark energy remains a tantalizing puzzle. Whether it was a silent partner during inflation or a latecomer to the cosmic stage, its influence, or lack thereof, could reshape our understanding of the universe's origins. And as we'll see in the next mystery, the fate of the universe itself may hinge on the answers we uncover. Now turning to the future of the cosmos, we find ourselves staring into one of the most profound questions in all of science. What is the ultimate fate of the universe? Dark energy, the mysterious force driving the universe's accelerated expansion, holds the key to this cosmic destiny. But depending on how dark energy behaves over time, the universe could meet its end in dramatically different ways. Let's explore the possibilities. One of the most dramatic scenarios is known as the Big Rip. Imagine dark energy growing stronger and stronger over billions of years, eventually overpowering all other forces in the universe. In this scenario, galaxies would be torn apart first, followed by stars, planets, and even atoms themselves. The fabric of space-time would stretch to its breaking point, leaving behind a universe of isolated particles unable to interact. It's a chilling vision, but one that remains a real possibility if dark energy's influence continues to intensify. On the other end of the spectrum lies the Big Freeze, also known as the heat death of the universe. In this scenario, dark energy maintains a steady presence, causing the universe to expand forever. Over time, galaxies would drift farther and farther apart, stars would burn out, and the cosmos would grow colder and darker. Eventually, the universe would reach a state of maximum entropy where no usable energy remains and all activity grinds to a halt. It's a quieter, slower end, but no less final. Between these two extremes, there are other possibilities. Some theories suggest that dark energy could weaken over time, allowing gravity to regain control and pull the universe back together in a big crunch. Others propose that dark energy might fluctuate, leading to cycles of expansion and contraction. Each of these scenarios paints a different picture of the universe's future, but they all hinge on one critical question: how does dark energy behave over cosmic timescales? The truth is, we don't yet know. Our current observations only give us a snapshot of dark energy's influence, and predicting its long-term effects requires a deeper understanding of its nature. Is dark energy constant, or does it evolve? Does it interact with other components of the universe, like dark matter? These are the questions that keep cosmologists up at night, and the answers could reshape our understanding of everything from the smallest particles to the largest structures in the cosmos. As we ponder the fate of the universe, one thing is clear: dark energy is not just a scientific curiosity, it's a force that will shape the destiny of everything we know. Whether the universe ends in a big rip, a big freeze, or something entirely unexpected, the story of dark energy is far from over. And as we'll see in the next mystery, the relationship between dark energy and dark matter could hold even more surprises. Now shifting our focus to the cosmic dance between two of the universe's most enigmatic forces, we arrive at the intriguing question of how dark energy and dark matter might interact. These two components make up the vast majority of the universe's energy and matter, yet they remain shrouded in mystery. While dark energy drives the accelerated expansion of the cosmos, dark matter acts as the invisible scaffolding that holds galaxies together. But do these two forces influence each other, and if so, how? At first glance, dark energy and dark matter seem to operate independently. Dark energy is thought to permeate all of space, exerting a repulsive force that pushes galaxies apart. Dark matter, on the other hand, is a gravitational glue, clustering around galaxies and providing the gravitational pull needed to keep them intact. But could there be more to their relationship? Some theories suggest that dark energy and dark matter might interact in subtle ways, influencing each other's behavior over cosmic timescales. One possibility is that dark energy and dark matter exchange energy, altering the rate at which the universe expands. For example, if dark energy were to transfer energy to dark matter, it could slow down the acceleration of the universe, potentially leading to a future where gravity regains dominance. Alternatively, if dark matter were to lose energy to dark energy, the expansion could accelerate even faster, bringing us closer to a big rip scenario. These interactions, if they exist, could fundamentally reshape our understanding of the universe's evolution. Another intriguing idea is that dark energy and dark matter might be two sides of the same cosmic coin. Some models propose that they could be different manifestations of a single underlying phenomenon, much like how electricity and magnetism are interconnected in electromagnetism. If true, this would mean that the behavior of one could directly affect the other, opening up new avenues for understanding the cosmos. However, detecting such interactions is no easy task. Current observations provide only indirect clues, and separating the effects of dark energy from those of dark matter requires incredibly precise measurements. Future missions like the Euclid telescope aim to map the distribution of dark matter and dark energy with unprecedented accuracy, potentially revealing whether these two forces are truly independent or if they share a deeper connection. As we explore this mystery, one thing becomes clear. The relationship between dark energy and dark matter is not just a scientific curiosity. It's a key piece of the puzzle in understanding the universe's past, present, and future. Whether they interact or not, their combined influence shapes the cosmos on the grandest scales, and unraveling their secrets could bring us closer to answering some of the most profound questions in science. And as we'll see in the next mystery, the Hubble tension adds yet another layer of complexity to our understanding of the universe's expansion. Now turning to one of the most puzzling challenges in modern cosmology, we encounter the Hubble tension, a discrepancy that has left scientists scratching their heads. At its core, the Hubble tension revolves around conflicting measurements of the Hubble constant, the rate at which the universe is expanding. On one hand, local observations of nearby galaxies and supernovas suggest a faster expansion rate. On the other, measurements from the cosmic microwave background, the afterglow of the Big Bang, point to a slower rate. This inconsistency isn't just a minor hiccup, it's a fundamental disagreement that could reshape our understanding of the cosmos. So, what's causing this tension? One possibility is that our current models of the universe are incomplete. Dark energy, the mysterious force driving the universe's accelerated expansion, might play a key role here. If dark energy behaves differently than we currently assume, perhaps changing over time or interacting with other components of the universe, it could explain why the expansion rate appears to vary depending on how we measure it. Alternatively, there could be unknown physics at play, such as new particles or forces that influence the universe's expansion in ways we haven't yet detected. Another angle to consider is the precision of our measurements. Local observations rely on techniques like measuring the brightness of supernova or the distances to nearby galaxies, while cosmic microwave background measurements depend on the early universe's conditions. Each method has its own set of uncertainties and potential biases, and reconciling them is no small feat. Some scientists suggest that systematic errors in our observations might be contributing to the tension, while others believe the discrepancy is a sign that our understanding of the universe's expansion needs a major overhaul. The implications of the Hubble tension are profound. If dark energy is indeed the culprit, it could mean that its properties are more complex than we've imagined, potentially opening the door to new theories about its nature. On the other hand, if the tension arises from unknown physics, it could lead to groundbreaking discoveries that challenge our current framework of cosmology. Either way, resolving this mystery is crucial for understanding not just how fast the universe is expanding, but also its ultimate fate. As we continue to refine our measurements and develop new tools, the Hubble tension remains a tantalizing puzzle, one that underscores the complexity of the cosmos and the limits of our current knowledge. And as we'll see in the next mystery, the concept of phantom energy takes this exploration of dark energy's mysteries to an even more speculative and fascinating level. Now shifting our gaze to an even more speculative corner of cosmology, we encounter the phantom energy hypothesis, a concept that takes the mystery of dark energy to a whole new level. Phantom energy is a hypothetical form of dark energy with a negative equation of state, meaning its energy density increases as the universe expands. This bizarre property sets it apart from other forms of dark energy and leads to some truly dramatic predictions about the fate of the cosmos. One of the most striking consequences of phantom energy is the possibility of a big rip. Unlike the Big Crunch, where the universe collapses back on itself, or the Big Freeze, where expansion slows to a halt, the Big Rip paints a far more violent picture. If phantom energy exists and continues to grow in strength, it could eventually overcome all forces holding the universe together, starting with galaxy clusters, then galaxies, stars, and even atoms themselves. In this scenario, the universe would tear itself apart in a catastrophic end, leaving behind nothing but isolated particles drifting in an ever-expanding void. But why is phantom energy considered speculative? For one, it challenges our current understanding of physics. A negative equation of state implies that phantom energy violates certain energy conditions that are fundamental to general relativity. While this doesn't rule it out entirely, it does make it a controversial idea. Additionally, there's no direct observational evidence for phantom energy yet. Its existence is inferred from theoretical models that attempt to explain the universe's accelerated expansion, but these models remain untested and highly debated. Despite its speculative nature, phantom energy is an intriguing possibility because it pushes the boundaries of what we think is possible in the cosmos. It forces us to question our assumptions about the nature of dark energy and the ultimate fate of the universe. Could phantom energy be real, or is it simply a mathematical curiosity that will fade as our understanding deepens? For now, it remains one of the most fascinating and unsettling ideas in modern cosmology. As we continue to explore the mysteries of dark energy, the phantom energy hypothesis serves as a reminder of how much we still have to learn. And as we'll see in the next mystery, the role of quantum vacuum energy adds yet another layer of complexity to this cosmic puzzle. Now turning to the enigmatic realm of quantum vacuum energy, we find ourselves grappling with one of the most profound puzzles in modern physics. Quantum vacuum energy, often referred to as zero-point energy, is the energy that exists in empty space even when it's completely devoid of matter or radiation. According to quantum field theory, the vacuum isn't truly empty, it's a seething, dynamic sea of virtual particles that constantly pop in and out of existence. This energy is thought to be a fundamental feature of the universe, but here's where things get puzzling. When scientists calculate the predicted energy density of the quantum vacuum, the result is staggeringly large, far larger than what we observe in the universe. This discrepancy is known as the cosmological constant problem, and it's one of the biggest unsolved mysteries in physics. The predicted value of quantum vacuum energy is off by a factor of around 1 followed by 120 zeros. That's an unimaginably huge difference, and it suggests that something fundamental is missing from our understanding of quantum field theory. If quantum vacuum energy were as strong as predicted, the universe would have torn itself apart long ago. Yet here we are, in a universe that's expanding at a rate that seems to require just the right amount of dark energy to match observations. So, what's going on? One possibility is that our calculations are missing a crucial piece of the puzzle. Perhaps there's a mechanism that cancels out most of the quantum vacuum energy, leaving behind the tiny amount we observe as dark energy. Another idea is that our understanding of quantum field theory is incomplete, and we need a new framework to explain why the vacuum energy is so much smaller than predicted. Some scientists even speculate that the quantum vacuum might not be the source of dark energy at all, but rather a separate phenomenon that we've yet to fully comprehend. This mystery isn't just a theoretical curiosity, it has profound implications for our understanding of the universe. If we can solve the puzzle of quantum vacuum energy, we might unlock new insights into the nature of dark energy, the fabric of space-time, and even the fundamental laws of physics. But for now, the gap between prediction and observation remains one of the most tantalizing challenges in cosmology. As we move forward, the next mystery will take us deeper into the cosmic web, exploring how dark energy shapes the large-scale structure of the universe and what it reveals about the forces driving its evolution. Now shifting our gaze to the vast cosmic tapestry, we delve into the intricate role dark energy plays in shaping the large-scale structure of the universe. Picture the cosmos as a colossal web, with galaxies and galaxy clusters forming dense nodes connected by filaments, while vast, empty regions known as cosmic voids stretch between them. This cosmic web is not static. It's a dynamic structure that has been evolving since the dawn of the universe, and dark energy is one of the key forces driving its transformation. Dark energy's influence becomes most apparent when we consider how it affects the expansion of the universe. As the universe expands, dark energy works against gravity, pushing galaxies apart and altering the way matter clumps together over time. In the early universe, gravity dominated, pulling matter into dense regions that eventually formed galaxies and clusters. But as dark energy began to dominate, it started to counteract gravity's pull, slowing the growth of these structures and even causing some to drift apart. One of the most striking features of the cosmic web is the presence of cosmic voids, enormous, nearly empty regions that can span hundreds of millions of light years. These voids are not just empty space, they are shaped by the interplay between dark energy and gravity. As dark energy accelerates the expansion of the universe, it stretches these voids even larger, creating a more pronounced contrast between the dense filaments and the empty spaces between them. Studying these voids provides crucial clues about the properties of dark energy, as their size and distribution are directly influenced by its effects. However, modeling the large-scale structure of the universe is no easy task. Scientists rely on sophisticated simulations that incorporate the effects of dark energy, dark matter, and ordinary matter, but even the most advanced models struggle to fully capture the complexity of the cosmic web. One of the biggest challenges is accounting for the subtle ways dark energy influences the growth of structures over billions of years. Small discrepancies in these models can lead to significant differences in how we understand the universe's evolution. Despite these challenges, observations of the cosmic web have already revealed fascinating insights. For instance, the distribution of galaxy clusters and voids aligns with predictions based on the presence of dark energy, providing strong evidence for its existence. Additionally, measurements of how quickly structures grow over time help constrain the properties of dark energy, such as its equation of state, a key parameter that describes how its density changes as the universe expands. As we continue to map the cosmic web with ever greater precision, we edge closer to unraveling the mysteries of dark energy. Each new observation brings us a step closer to understanding how this enigmatic force shapes the universe on the largest scales. And as we turn our attention to the next mystery, we'll explore how dark energy might influence the propagation of gravitational waves, offering yet another window into its elusive nature. Now turning to one of the most critical tools in understanding dark energy, we explore the equation of state parameter, often denoted as W. This parameter is essentially a measure of how dark energy behaves as the universe expands. Think of it as a fingerprint that helps scientists identify the nature of dark energy. If W equals -1, it suggests that dark energy behaves like a cosmological constant, a form of energy that remains uniform over time. However, if W deviates from -1, it could indicate that dark energy is dynamic, changing in strength as the universe evolves. The significance of this parameter lies in its ability to shape our understanding of the universe's fate. For instance, if W is exactly -1, the universe will continue to expand at an accelerating rate, leading to a big freeze scenario where galaxies drift apart and the cosmos grows colder and emptier. But if W is less than -1, it could point to a more dramatic outcome, such as the Big Rip, where dark energy becomes so dominant that it tears apart galaxies, stars, and even atoms. Determining the exact value of W is no small feat. Observations from supernova, galaxy clusters, and the cosmic microwave background all provide clues, but they often yield slightly different results. These discrepancies make it challenging to pin down the precise value of W, leaving scientists with a range of possibilities rather than a definitive answer. This uncertainty is one of the reasons why dark energy remains such a profound mystery. Efforts to constrain W rely on cutting-edge technology and innovative methods. For example, the Euclid Space Telescope and the Vera C, Rubin Observatory are designed to measure the distribution of galaxies and the rate of cosmic expansion with unprecedented precision. These observations aim to narrow down the possible values of W, bringing us closer to understanding whether dark energy is constant or evolving. Yet, even with these advancements, the exact value of W remains elusive. Part of the challenge lies in the subtlety of dark energy's effects. Unlike gravity, which dominates on smaller scales, dark energy's influence becomes significant only over vast cosmic distances. This makes it incredibly difficult to measure directly, requiring observations that span billions of light years. As we continue to refine our measurements and develop new techniques, the equation of state parameter remains a central focus in the quest to unravel the mysteries of dark energy. Each new observation brings us closer to understanding this enigmatic force, and with it, the ultimate fate of our universe. And as we move forward, we'll explore how dark energy might interact with another cosmic mystery, gravitational waves, offering yet another perspective on its elusive nature. Now shifting our focus to a fascinating alternative perspective, let's explore the role of modified gravity theories in explaining the universe's accelerating expansion. While dark energy remains the leading explanation, some scientists propose that the acceleration might not be due to an unknown energy form, but rather a modification of our understanding of gravity itself. These theories, such as F of R gravity, suggest that Einstein's theory of general relativity might need adjustments on cosmic scales to account for the observed acceleration. Modified gravity theories aim to explain the universe's expansion without invoking dark energy. Instead of attributing the acceleration to a mysterious force, these theories propose that gravity behaves differently on large scales than it does in smaller, more familiar settings. For example, F of R gravity introduces a new function of the curvature of spacetime, altering how gravity operates over vast distances. This could potentially explain why galaxies appear to be moving apart faster than expected without the need for dark energy. However, these theories face significant challenges. One of the biggest hurdles is matching observations. While modified gravity can explain cosmic acceleration, it must also account for other phenomena, such as the behavior of galaxy clusters and the cosmic microwave background. So far, no modified gravity theory has been able to fully replicate the success of the dark energy model in explaining all observed data. This discrepancy leaves scientists grappling with whether modified gravity is a viable alternative or if dark energy remains the more plausible explanation. Another challenge lies in testing these theories. Unlike dark energy, which can be indirectly observed through its effects on the universe's expansion, modified gravity requires precise measurements of gravitational interactions on cosmic scales. This is no easy task, as gravity's influence becomes incredibly subtle over such vast distances. Current and future missions, like the Euclid telescope, aim to provide more data to test these theories, but for now, the debate remains unresolved. Despite these challenges, modified gravity theories offer a compelling alternative that challenges our fundamental understanding of the universe. They remind us that science thrives on questioning established ideas and exploring new possibilities. As we continue to gather data and refine our models, the question of whether dark energy or modified gravity holds the key to cosmic acceleration remains one of the most intriguing mysteries in modern cosmology. And as we move forward, we'll delve into another cosmic puzzle: how dark energy might have influenced the early universe during the era of cosmic inflation. Now turning to the early moments of the universe, we find ourselves exploring the intriguing possibility that dark energy might have played a role during the era of cosmic inflation. This period, just fractions of a second after the Big Bang, saw the universe expand exponentially, setting the stage for the cosmos we observe today. But could dark energy, the mysterious force driving the universe's current acceleration, have also influenced this ancient expansion? cosmic inflation is a well-supported theory that explains the uniformity and structure of the universe. It proposes that a brief but intense burst of expansion smoothed out the early universe and planted the seeds for galaxies and large-scale structures. However, the exact mechanism behind inflation remains a mystery. Some scientists speculate that dark energy or something like it might have been at work during this epoch. If true, this would suggest a deep connection between the universe's earliest moments and its present-day behavior. One of the biggest challenges in connecting dark energy to inflation is the vast difference in scale and energy. The inflationary epoch involved energies far beyond anything we can replicate or observe directly, while dark energy operates on much larger cosmological scales. Bridging these two eras requires a theoretical framework that can explain how a force like dark energy could manifest in such different contexts. This is no small task, as it would require rethinking some of the most fundamental aspects of physics. Another hurdle is the lack of direct evidence. While the cosmic microwave background provides a snapshot of the universe just after inflation, it doesn't offer clear clues about dark energy's potential role. Detecting any influence of dark energy during inflation would require new observational tools or breakthroughs in theoretical physics. Until then, this idea remains a tantalizing but speculative possibility. If dark energy did play a role in inflation, it would revolutionize our understanding of cosmic history. It could mean that the same force driving the universe's expansion today also shaped its earliest moments, creating a unified narrative of cosmic evolution. This would not only deepen our understanding of dark energy, but also provide new insights into the nature of the universe itself. As we continue to probe the mysteries of dark energy and cosmic inflation, we are reminded of how much remains to be discovered. The connection between these two eras, if it exists, could unlock profound truths about the universe's origins and destiny. And as we move forward, we'll explore another cosmic enigma: how dark energy might relate to the concept of the multiverse and the fine-tuning of our universe for life. Now shifting our gaze to the vast and speculative realm of the multiverse, we encounter a fascinating possibility. Could the existence of multiple universes help explain the peculiar value of dark energy in our own? The multiverse theory suggests that our universe might be just one of countless others, each with its own unique set of physical laws and constants. In this cosmic landscape, the value of dark energy in our universe might not be a random accident, but rather a consequence of the broader multiverse framework. One intriguing idea tied to the multiverse is the anthropic principle, which posits that the conditions in our universe are just right for life to exist because, well, we're here to observe them. If there are countless universes with varying properties, it's possible that only those with the right balance of dark energy and other factors could support life. In this view, our universe's dark energy density might seem fine-tuned because it falls within the narrow range that allows galaxies, stars, and planets to form and ultimately life to emerge. But why does dark energy's value matter so much? If dark energy were significantly stronger, the universe would have expanded too quickly for structures like galaxies to form. If it were weaker, gravity might have caused the universe to collapse back on itself long before life could arise. The fact that dark energy's density is just right for our existence has led some scientists to wonder if the multiverse could provide an explanation. In a sea of universes with different dark energy values, ours might simply be one of the lucky ones where conditions are perfect for life. This idea, while compelling, is not without its challenges. The multiverse remains a highly speculative concept with no direct evidence to confirm its existence. Additionally, the anthropic principle raises philosophical questions about the nature of science and observation. Can we rely on the fact that we exist to explain the properties of our universe, or does this approach sidestep the deeper question of why these properties exist in the first place? Despite these uncertainties, the multiverse hypothesis offers a tantalizing way to think about dark energy and its role in our universe. It suggests that the mysteries of dark energy might not be confined to our cosmos alone, but could be part of a much larger, interconnected reality. As we continue to explore the frontiers of cosmology, the multiverse remains a bold and imaginative framework that challenges us to rethink our place in the grand tapestry of existence. With this cosmic puzzle in mind, we now turn to another intriguing question: how does dark energy influence the formation and evolution of galaxies, the building blocks of our universe? This connection holds the key to understanding how dark energy shapes the cosmos on both the largest and smallest scales. Now shifting our focus to the intricate dance of galaxies, we explore how dark energy plays a pivotal role in their formation and evolution. Galaxies, the majestic islands of stars, gas, and dust, are not just static structures but dynamic entities shaped by the forces of the cosmos. Among these forces, dark energy exerts a subtle yet profound influence, subtly altering the way galaxies come together and grow over billions of years. In a universe dominated by dark energy, the expansion of space itself accelerates, creating a cosmic tug of war between the pull of gravity and the push of dark energy. This acceleration affects how matter clumps together, influencing the formation of galaxies. Early in the universe's history, gravity was the dominant force, pulling matter into dense regions that eventually collapsed to form galaxies. But as dark energy began to dominate, it started to counteract gravity's pull, slowing the growth of these structures and shaping the large-scale architecture of the cosmos. One of the key challenges in understanding this process lies in modeling galaxy formation in a dark energy-dominated universe. Simulations must account for the complex interplay between gravity, dark energy, and the various processes that occur within galaxies, such as star formation, supernova explosions, and the feedback from supermassive black holes. These simulations reveal that dark energy not only slows the growth of galaxies but also influences their distribution, creating vast cosmic voids and intricate webs of filaments that define the universe's large-scale structure. Observations of distant galaxies provide further insights into dark energy's role. By studying how galaxies cluster and evolve over time, astronomers can trace the impact of dark energy on the universe's expansion. For instance, the distribution of galaxy clusters today compared to their distribution billions of years ago offers clues about how dark energy has shaped the cosmos. These observations align with the predictions of our current models, but they also raise new questions. Why, for example, do some galaxies seem to form earlier or more efficiently than expected in a dark energy-dominated universe? And how does dark energy influence the intricate processes within galaxies, such as the birth and death of stars? As we delve deeper into these mysteries, it becomes clear that dark energy is not just a passive backdrop, but an active participant in the cosmic drama of galaxy formation. Its influence extends from the largest scales of the universe down to the intricate details of how galaxies evolve and interact. Understanding this connection is crucial for piecing together the full story of our universe's history and its ultimate fate. With this in mind, we now turn our attention to another frontier in the study of dark energy, the search for its presence in laboratory experiments. Could we detect dark energy not just in the vastness of space, but also within the controlled confines of a lab? This question opens up new possibilities for unraveling one of the greatest mysteries of the cosmos. Now turning to the realm of human ingenuity, we explore the fascinating efforts to detect dark energy not in the vastness of space, but within the controlled environments of laboratories. While dark energy's effects are most evident on cosmic scales, scientists are pushing the boundaries of technology to uncover its presence in the microscopic world. This pursuit is as ambitious as it is challenging, requiring precision and innovation to measure forces that are incredibly subtle yet potentially transformative for our understanding of the universe. One promising avenue in this search involves the Casimir effect, a phenomenon where two uncharged metal plates placed extremely close together experience an attractive force due to quantum fluctuations in the vacuum of space. This effect, though tiny, is a direct consequence of the quantum vacuum, which some theories suggest could be linked to dark energy. By measuring the Casimir effect with unprecedented accuracy, researchers hope to detect deviations that might hint at the influence of dark energy. However, these experiments are incredibly delicate, requiring isolation from even the slightest external disturbances, such as vibrations or temperature changes. Another approach focuses on testing gravity at very small scales. According to Einstein's theory of general relativity, gravity behaves predictably across vast distances, but at microscopic scales, its behavior might differ due to the presence of dark energy or other unknown forces. Experiments using ultra-sensitive instruments such as torsion balances or atom interferometers aim to detect any anomalies in gravitational interactions at these tiny scales. These tests could reveal whether dark energy leaves a fingerprint in the fabric of spacetime itself, even in the confines of a laboratory. The challenges of these experiments are immense. Dark energy's effects are so faint that they are easily drowned out by background noise or experimental uncertainties. Moreover, the theoretical predictions about how dark energy might manifest in these settings are still speculative, making it difficult to design experiments with clear targets. Despite these hurdles, the potential rewards are enormous. Successfully detecting dark energy in a lab would not only confirm its existence, but also provide critical insights into its nature and how it interacts with the fundamental forces of the universe. As we continue to refine these experiments, the search for dark energy in the lab represents a bold fusion of cosmology and quantum physics. It's a reminder that some of the universe's greatest mysteries might be hiding not in the distant cosmos, but right here on Earth, waiting to be uncovered through human curiosity and ingenuity. With this in mind, we now shift our gaze to another intriguing question: how dark energy might be connected to the very nature of time itself. Now shifting our focus to the enigmatic relationship between dark energy and time, we delve into one of the most speculative yet fascinating mysteries in cosmology. Could dark energy, the force driving the universe's accelerated expansion, be intrinsically linked to the very fabric of time itself? This question challenges our understanding of both cosmology and the nature of time, opening the door to profound possibilities. One intriguing idea is the concept of time-varying dark energy. Unlike the traditional view of dark energy as a constant force, this theory suggests that dark energy's strength could change over time. If true, this would mean that the rate of the universe's expansion isn't just accelerating, it's doing so in a way that evolves as time progresses. Such a scenario would have dramatic implications for the fate of the cosmos. For instance, if dark energy grows stronger over time, it could lead to a big rip where galaxies, stars, and even atoms are torn apart. On the other hand, if dark energy weakens, the universe's expansion might slow down, potentially leading to a different cosmic destiny. But how could dark energy and time be connected? Some theories propose that dark energy might influence the flow of time itself. In this speculative framework, dark energy could act as a kind of cosmic clock, shaping the rate at which time progresses on a universal scale. This idea ties into the broader question of whether time is a fundamental property of the universe or an emergent phenomenon arising from deeper physical laws. If dark energy plays a role in this process, it could revolutionize our understanding of both time and the cosmos. Another angle explores the possibility that dark energy's influence on time could be detectable through subtle changes in the universe's expansion rate over billions of years. By studying the cosmic microwave background, the distribution of galaxies, and other large-scale structures, scientists hope to find clues about whether dark energy's effects have varied over time. These observations could provide indirect evidence of a connection between dark energy and time, even if the exact mechanism remains elusive. While these ideas are still speculative, they highlight the profound questions that dark energy raises about the nature of reality. If dark energy and time are indeed linked, it would mean that the universe's expansion isn't just a physical process, it's a temporal one as well, deeply intertwined with the flow of time itself. As we continue to explore these mysteries, we may uncover insights that reshape our understanding of both the cosmos and the passage of time. With this thought-provoking connection in mind, we now turn our attention to another cosmic puzzle: how dark energy influences the growth and properties of cosmic voids, the vast empty regions that stretch between galaxies. Now turning to the vast, empty expanses of the universe, we explore the role of dark energy in shaping cosmic voids, the enormous regions of space that lie between galaxy clusters. These voids, often spanning hundreds of millions of light years, are not just empty spaces but key players in understanding the large-scale structure of the cosmos. Dark energy, the mysterious force driving the universe's accelerated expansion, plays a crucial role in how these voids form and evolve over time. Cosmic voids are like the negative space in a cosmic painting, defining the boundaries and structure of the universe's web-like arrangement. As dark energy pushes galaxies apart, it also influences the growth of these voids, causing them to expand and become even emptier over time. This process is not just a passive effect but an active one, as dark energy's repulsive force counteracts the gravitational pull of matter, preventing galaxies from clustering too densely and allowing voids to grow larger. One of the most fascinating aspects of cosmic voids is what they reveal about dark energy's properties. By studying the size, distribution, and growth rate of these voids, scientists can gain insights into how dark energy behaves on the largest scales. For example, if dark energy's strength changes over time, as some theories suggest, this would leave a detectable imprint on the evolution of cosmic voids. Observations of these regions could provide critical clues about whether dark energy is constant or dynamic, helping to refine our understanding of its nature. Moreover, cosmic voids serve as natural laboratories for testing theories of gravity and the universe's expansion. Because these regions contain so little matter, they are less affected by the complex interactions that dominate galaxy clusters, making them ideal for studying the effects of dark energy in a relatively clean environment. By mapping the distribution of voids and analyzing their growth, researchers can compare their findings with predictions from different cosmological models, shedding light on the true nature of dark energy. The study of cosmic voids also highlights the interconnectedness of the universe's large-scale structure. Voids are not isolated features but part of a cosmic web that includes filaments, nodes, and clusters. Dark energy's influence on voids ripples through this web, shaping the overall architecture of the universe. Understanding how voids grow and evolve helps us piece together the broader story of cosmic evolution from the early universe to the present day. As we continue to probe the mysteries of cosmic voids, we uncover new layers of insight into dark energy's role in shaping the cosmos. These vast, empty regions may seem like the absence of structure, but they are, in fact, a vital piece of the puzzle in our quest to understand the universe's expansion and ultimate fate. With this exploration of voids in mind, we now shift our focus to another intriguing question: how dark energy might influence the propagation of gravitational waves, the ripples in space-time caused by cataclysmic cosmic events. Now shifting our gaze to the ripples that travel through the fabric of space-time, we delve into the intriguing relationship between dark energy and gravitational waves. These waves, first predicted by Albert Einstein over a century ago, are disturbances caused by some of the most energetic events in the universe, such as the collision of black holes or the merging of neutron stars. But how does dark energy, the force driving the universe's accelerated expansion, influence these cosmic ripples? Gravitational waves are like messengers from the distant cosmos, carrying information about the events that created them. As they travel across the universe, their journey is shaped by the very structure of spacetime itself. Dark energy, by altering the rate at which the universe expands, could subtly affect how gravitational waves propagate. For instance, if dark energy's strength changes over time, it might leave a faint imprint on the waves, altering their frequency or amplitude by the time they reach us. This means that gravitational waves could serve as a new tool for probing the properties of dark energy, offering insights that traditional observations of light cannot provide. One of the most exciting possibilities is that future gravitational wave detectors, like the planned Laser Interferometer Space Antenna, or LISA, could detect these subtle effects. By analyzing how gravitational waves from distant events behave as they travel through the expanding universe, scientists might uncover clues about whether dark energy is constant or evolving. This would be a groundbreaking discovery, as it could help us determine whether dark energy is a fixed property of space, like Einstein's cosmological constant, or something more dynamic, such as a field that changes over time. Moreover, gravitational waves could also help us test alternative theories of gravity. Some models propose that what we perceive as dark energy might actually be a sign that our understanding of gravity is incomplete. By studying how gravitational waves interact with the large-scale structure of the universe, researchers could compare these observations with predictions from different theories, potentially ruling out some explanations while supporting others. This would bring us closer to solving one of the greatest mysteries in modern cosmology. The interplay between dark energy and gravitational waves opens up a new frontier in our exploration of the universe. These ripples in space-time not only reveal the violent events that created them, but also carry subtle hints about the nature of the cosmos itself. As we continue to refine our ability to detect and analyze gravitational waves, we may find that they hold the key to unlocking the secrets of dark energy, shedding light on the forces that shape the universe's past, present, and future. With this in mind, we now turn to another fascinating question: how dark energy influences the cosmic microwave background, the faint afterglow of the Big Bang. Now turning to the faint afterglow of the Big Bang, we explore how dark energy leaves its mark on the cosmic microwave background, or CMB. This ancient light, which fills the entire universe, is like a snapshot of the cosmos when it was just 380,000 years old. It holds clues not only about the early universe, but also about the forces that have shaped its evolution over billions of years, including dark energy. The CMB is incredibly uniform, but tiny fluctuations in its temperature and density reveal the seeds of the large-scale structures we see today, like galaxies and galaxy clusters. Dark energy, by driving the accelerated expansion of the universe, influences how these structures grow and evolve, but detecting its direct imprint on the CMB is no easy task. The effects of dark energy are subtle, often buried within the complex interplay of gravity, matter, and radiation. One way dark energy might influence the CMB is through its impact on the universe's geometry. According to Einstein's theory of general relativity, the amount and distribution of energy in the universe determine its shape, whether it's flat, open, or closed. Dark energy, by contributing to the total energy density, affects this geometry. Precise measurements of the CMB's temperature fluctuations can reveal whether the universe is flat, which would align with the predictions of a dark energy-dominated cosmos. Another potential signature of dark energy in the CMB lies in the way it affects the growth of cosmic structures. As dark energy accelerates the expansion of the universe, it suppresses the formation of large-scale structures over time. This suppression leaves a subtle imprint on the CMB's polarization patterns, which are created by the scattering of light-off electrons in the early universe. By studying these patterns, scientists can infer how dark energy has influenced the growth of structures across cosmic history. However, detecting these subtle effects is a significant challenge. The CMB is already incredibly faint, and the signals linked to dark energy are even fainter. Current observatories like the Planck satellite have provided us with a wealth of data, but they are limited in their ability to measure the tiny distortions caused by dark energy. Future missions such as the Simons Observatory and the CMB Stage 4 project aim to achieve unprecedented precision, potentially uncovering new insights into dark energy's role in shaping the universe. These next-generation experiments could also help us distinguish between different models of dark energy. For example, if dark energy is not a constant force but evolves over time, its effects on the CMB would differ from those predicted by the cosmological constant. By comparing observations with theoretical predictions, scientists could determine whether dark energy is static or dynamic, bringing us closer to understanding its true nature. The cosmic microwave background is more than just a relic of the early universe. It's a window into the forces that have shaped the cosmos over billions of years. As we continue to refine our measurements and develop new technologies, the CMB may hold the key to unraveling the mysteries of dark energy, shedding light on one of the most profound questions in modern cosmology. With this in mind, we now shift our focus to another intriguing possibility: whether dark energy could be decaying over time, altering the fate of the universe itself. Now shifting our gaze to a fascinating and speculative idea, let's explore the possibility that dark energy might not be a constant force but could instead decay over time. This concept challenges the traditional view of dark energy as a static entity, like the cosmological constant, and opens up a new realm of possibilities for the fate of the universe. If dark energy were to weaken or change over billions of years, it could dramatically alter the trajectory of cosmic expansion, leading to outcomes far different from what we currently predict. The idea of decaying dark energy stems from the observation that the universe's expansion rate has not always been the same. In the early universe, gravity dominated, slowing down the expansion. Then, around 5 billion years ago, dark energy began to take over, accelerating the expansion. But what if this acceleration isn't permanent? What if dark energy's influence diminishes over time? This would mean that the universe's expansion could slow down again, or even reverse, potentially leading to a Big Crunch scenario where everything collapses back into a single point. Testing this hypothesis is no small feat. One way scientists could detect a change in dark energy is by observing distant supernovae. These cosmic explosions serve as standard candles, allowing us to measure the expansion rate of the universe at different points in time. If dark energy were decaying, we would expect to see deviations from the predicted brightness of these supernovae, indicating a change in the expansion rate. Similarly, precise measurements of the cosmic microwave background and the large-scale structure of the universe could reveal subtle shifts in dark energy's influence over cosmic history. Another intriguing possibility is that decaying dark energy could leave a unique fingerprint on the distribution of galaxies and galaxy clusters. As dark energy weakens, its ability to suppress the growth of large-scale structures would diminish, potentially leading to a faster-than-expected formation of cosmic webs. By mapping the universe's structure in unprecedented detail, future missions like the Euclid Telescope and the Vera-C Rubin Observatory could provide crucial evidence for or against this idea. The implications of decaying dark energy are profound. If confirmed, it would mean that the universe's fate is far more dynamic and uncertain than we currently imagine. Instead of a relentless expansion leading to a big freeze, where galaxies drift apart forever, we might face a universe that contracts, collapses, or even cycles through periods of expansion and contraction. This would not only reshape our understanding of dark energy, but also challenge our fundamental theories of physics and cosmology. As we continue to probe the mysteries of dark energy, the possibility of its decay remains one of the most tantalizing questions in modern science. Future observations and experiments will be key to uncovering whether dark energy is truly constant or if it evolves over time, offering us a deeper glimpse into the ultimate destiny of the cosmos. With this in mind, we now turn our attention to another captivating mystery: how dark energy might influence the formation of supermassive black holes, the giants that lurk at the hearts of galaxies. Now turning to the enigmatic giants of the cosmos, let's explore the role of dark energy in the formation of supermassive black holes. These colossal structures, found at the centers of galaxies, have long puzzled scientists with their immense size and mysterious origins. Could dark energy, the force driving the universe's accelerated expansion, have played a part in their creation? This question opens a fascinating window into the interplay between the largest and smallest scales of the cosmos. Supermassive black holes, some weighing billions of times the mass of our Sun, are thought to form through a combination of processes, including the collapse of massive gas clouds and the merging of smaller black holes. However, the exact mechanisms behind their rapid growth remain unclear. One intriguing possibility is that dark energy, by influencing the expansion rate of the universe, may have indirectly shaped the environments in which these black holes formed. For instance, during periods when dark energy's influence was weaker, gravity could have dominated more effectively, allowing matter to clump together and form the seeds of supermassive black holes. Connecting dark energy to black hole formation is no simple task. One of the biggest challenges lies in the vast timescales involved. The growth of supermassive black holes spans billions of years, making it difficult to trace their evolution and pinpoint the role of dark energy. Additionally, dark energy's effects are most noticeable on the largest scales of the universe, while black hole formation occurs on much smaller galactic scales. Bridging this gap requires sophisticated models and simulations that can account for both the cosmic expansion and the intricate dynamics of galaxy formation. Another layer of complexity comes from the fact that dark energy's influence is subtle and cumulative. Unlike gravity, which acts directly on matter, dark energy's primary effect is to stretch the fabric of space itself. This means its impact on black hole formation would be indirect, shaping the conditions in which galaxies and their central black holes evolve. For example, if dark energy were to weaken over time, as some theories suggest, it could alter the rate at which galaxies merge, potentially affecting the growth of supermassive black holes. Despite these challenges, scientists are making progress. Observations of distant quasars, the bright cores of galaxies powered by supermassive black holes, provide clues about how these objects grew in the early universe. By studying the distribution and properties of quasars across cosmic time, researchers can infer how dark energy may have influenced their formation. Similarly, advanced simulations that incorporate dark energy's effects are helping to shed light on the complex interplay between cosmic expansion and black hole growth. The implications of this research are profound. If dark energy played a role in the formation of supermassive black holes, it would mean that the universe's largest structures are deeply connected to its most mysterious force. This could reshape our understanding of cosmic evolution, revealing how the expansion of the universe and the growth of galaxies are intertwined. As we continue to unravel these mysteries, we move closer to understanding the full story of how the cosmos came to be. With this in mind, we now shift our focus to another captivating aspect of dark energy's influence, its role in shaping the cosmic web, the vast network of filaments and voids that define the universe's large-scale structure. Now shifting our gaze to the grand tapestry of the cosmos, let's delve into how dark energy influences the cosmic web, the sprawling network of filaments and voids that define the universe's large-scale structure. This intricate framework, often likened to a cosmic spiderweb, is the result of billions of years of gravitational interactions, with dark energy playing a subtle yet profound role in its evolution. The cosmic web is made up of dense filaments of galaxies and gas, separated by vast, nearly empty voids. These filaments act as the highways of the universe, connecting galaxy clusters and feeding them with matter. But how does dark energy, a force that stretches space itself, shape this colossal structure? The answer lies in its influence on the universe's expansion rate. As dark energy accelerates the expansion, it affects how matter clumps together over time. In the early universe, gravity dominated, pulling matter into dense regions and forming the seeds of the cosmic web. However, as dark energy's influence grew, it began to counteract gravity's pull, slowing the growth of these structures and shaping the web we see today. Simulations of the universe's evolution provide a fascinating glimpse into this process. By modeling the effects of dark energy alongside gravity, scientists can recreate the formation of the cosmic web over billions of years. These simulations reveal that dark energy not only slows the growth of filaments but also influences the size and distribution of voids. For instance, as dark energy accelerates expansion, voids grow larger, stretching the filaments that connect them. This creates a delicate balance between the forces of gravity and dark energy, shaping the cosmic web into its current form. Observations of the cosmic web further support these findings. By mapping the distribution of galaxies and measuring the cosmic microwave background, astronomers can trace the imprint of dark energy on the universe's large-scale structure. One striking discovery is that the cosmic web appears more stretched and diffuse in regions where dark energy's influence is stronger. This aligns with the idea that dark energy not only drives the universe's expansion, but also leaves its mark on the very fabric of cosmic structure. The implications of this are profound. If dark energy shapes the cosmic web, it means that the universe's largest structures are intimately connected to its most mysterious force. This connection offers a unique window into the nature of dark energy itself. By studying the cosmic web, scientists can test theories about dark energy's properties, such as whether it remains constant over time or evolves in strength. These insights could help unravel one of the greatest mysteries in cosmology: what dark energy truly is. As we continue to explore the cosmic web, we uncover not just the structure of the universe, but also the forces that have shaped it. This intricate interplay between dark energy and gravity has sculpted the cosmos into the vast, interconnected network we observe today. And as our understanding deepens, we move closer to answering some of the most fundamental questions about the universe's past, present, and future. With this in mind, we now turn to the final chapter of our exploration, the future of dark energy research and the exciting discoveries that lie ahead. As we step into the final chapter of our cosmic journey, let's explore the future of dark energy research and the groundbreaking discoveries that await us. Despite decades of study, dark energy remains one of the most profound mysteries in science, and the quest to understand it is far from over. Today, we stand on the brink of a new era in cosmology, armed with advanced tools and technologies that promise to unlock the secrets of this enigmatic force. The current state of dark energy research is both exciting and humbling. While we've made significant strides in mapping its effects on the universe's expansion and large-scale structure, fundamental questions remain unanswered. What is the true nature of dark energy? Is it a constant force, or does it evolve over time? And how does it interact with other cosmic components like dark matter? These questions drive the next generation of experiments and missions, each designed to peel back another layer of the cosmic mystery. One of the most anticipated projects is the Euclid telescope, a European Space Agency mission set to launch in the coming years. Euclid will map the distribution of galaxies and cosmic structures across more than 1/3 of the sky, providing unprecedented insights into the effects of dark energy. By measuring the shapes and positions of billions of galaxies, Euclid aims to trace the history of the universe's expansion with remarkable precision. This data could reveal whether dark energy has changed over time, offering clues to its true nature. Another game changer is the Vera C. Rubin Observatory, currently under construction in Chile. This observatory will conduct the Legacy Survey of Space and Time, a 10-year project that will capture detailed images of the night sky. By observing billions of galaxies and tracking their movements, the Rubin Observatory will help scientists measure the rate of cosmic expansion and the growth of large-scale structures. Its findings could shed light on whether dark energy behaves as predicted by the cosmological constant, or if alternative theories like modified gravity are needed to explain its effects. These missions are complemented by ground-based experiments, such as the Dark Energy Spectroscopic Instrument, or DESI, which is mapping the three-dimensional distribution of galaxies. By studying the clustering of galaxies and the patterns of cosmic voids, DESI aims to provide new constraints on dark energy's properties. Together, these projects represent a coordinated effort to tackle one of the greatest challenges in modern science. But the future of dark energy research isn't just about new tools, it's also about new ideas. Scientists are exploring innovative theories, from evolving dark energy models to the possibility of interactions between dark energy and dark matter. Some are even investigating whether dark energy could be connected to the nature of time itself. These bold ideas push the boundaries of our understanding, challenging us to think beyond the limits of current knowledge. As we look ahead, one thing is clear: the journey to unravel the mysteries of dark energy is far from over. Each new discovery brings us closer to understanding the forces that shape our universe, and with every step we uncover more questions to explore. The future of dark energy research is not just about finding answers, it's about embracing the unknown and continuing to push the frontiers of human knowledge. And so, as we conclude our exploration of the 25 mysteries of the cosmic dark energy era, we invite you to stay curious and follow the unfolding story of the cosmos. The universe is full of wonders waiting to be discovered, and the next great revelation could be just around the corner. Thank you for joining us on this journey, and don't forget to subscribe for more space mysteries and cosmic adventures. Until next time, keep looking up. As we bring our exploration of the 25 mysteries of the cosmic dark energy era to a close, let's take a moment to reflect on the incredible journey we've shared. From the accelerating expansion of the universe to the enigmatic nature of dark energy itself, each mystery has revealed just how much we still have to learn about the cosmos. These questions aren't just scientific puzzles, they're windows into the very fabric of reality, challenging us to rethink our understanding of space, time, and existence. The significance of these mysteries cannot be overstated. They shape our understanding of the universe's past, present, and future, from the formation of galaxies to the ultimate fate of everything we see. Dark energy, in particular, stands as one of the most profound enigmas in science, a force that defies easy explanation yet holds the key to unlocking the secrets of cosmic evolution. As we've seen, the quest to understand it has driven some of the most ambitious scientific endeavors in history, from groundbreaking telescopes to innovative theories that push the boundaries of human knowledge. But the story doesn't end here. The mysteries of dark energy are far from solved, and the journey to uncover their secrets is just beginning, with new missions like the Euclid telescope and the Vera C. Rubin Observatory on the horizon. We're poised to make discoveries that could revolutionize our understanding of the universe. The future of cosmology is bright, and every new observation, every new theory, brings us one step closer to unraveling the cosmic puzzle. As we conclude, we invite you to stay curious and keep exploring. The universe is full of wonders waiting to be discovered, and the next great revelation could be just around the corner. If you've enjoyed this journey through the mysteries of dark energy, Don't forget to share your thoughts and questions in the comments below. What fascinates you most about the cosmos? Which mystery do you hope scientists will solve next? Let's keep the conversation going. And if you're eager for more cosmic adventures, be sure to subscribe and hit the notification bell so you never miss an update. From the depths of black holes to the farthest reaches of the universe, there's always more to explore. Thank you for joining us on this incredible journey through the mysteries of the cosmic dark energy era. Until next time, keep looking up because the universe is waiting to reveal its secrets.